Good morning, folks, and welcome back for week 13 of IFSTA's Building Construction for the Fire Service. This week you'll be looking at Chapter 12 in the IFSTA book, which deals with special structures. And specifically, this chapter looks at high-rise occupancies, tensile structures, inflated structures, high-rack storage, kind of special adaptations of existing buildings where particularly interesting fire control problems exist. I've posted a number of resources in this week's materials, one of which is this Underwriter's Laboratory residential fire modeling site. And this is an optional activity for you. This would probably take you a couple of hours to get through, but this would look at how the scientists and engineers at Underwriter's Laboratory model fire in a single-family residence. And one of the things that you're going to see illustrated in this is that there's really nothing in a single-family residence that's particularly challenging in terms of fire control. Every fire today in a compartment is an oxygen-limited fire. The amount of fuel that's available for combustion in the modern single-family residence far exceeds the amount of air that's available to participate in combustion. What this means is that compartment size is really critical in terms of how large of a fire is capable of developing. Because single-family residences tend to have relatively small compartments, the fire control problem is really not terribly sophisticated. When you get into some of the large spaces that you're going to read about in this week's chapter, things like atriums, large high-rack storage warehouses, large open-span structures, for instance, assembly occupancies for sports arenas and that type of thing, this is a much more challenging fire control problem from an engineering perspective. So if you want to get a basis in kind of modeling in a single-family residence with small compartments, the UL seminar is a great place to start. And then the chapter in IFSTA will give you kind of the other side of the coin, which is the large commercial and institutional occupancies. When you've completed reading Chapter 12, there is a quiz on the chapter here that you'll need to complete, just like every other week. And additionally, you need to be working on your NCST research paper this week. Now, I have been looking through the gradebook. I see that many people have submitted proximate causes and contributory causes, and I'm working through grading those responses at this point. So you can expect feedback on those that have been submitted this week. The assignment that will be due at the end of week 13 is to discuss root causes. And remember, we've talked in previous videos about how there's this chain of causation from the bad event kind of back in time, and there are proximate causes, those causes that are immediately right next to the bad event, and then there are contributory causes, those are the causes that kind of caused the proximate causes, and then there are root causes. And remember that the designation of something as a proximate or a contributory or a root cause is somewhat arbitrary. That's really kind of in the eye of the beholder. The characteristic of root causes is that if you fix them, you fix the problem permanently. And as you saw in some of our earlier analysis, there's kind of this relationship in terms of the amount of resources consumed to fix the problem and how long the fix lasts. So root causes tend to be expensive to fix, but they tend to fix the problem on a permanent basis. One of the things that I've included as a resource for you here is a voice thread with an analysis from a chapter in a book that we use in the face-to-face version of this class by Mario Salvadori and his co-author Levy, where they analyze root causes of construction failures. And they've gotten it down to 5 root causes. And I think, if nothing else, this is a short voice thread. It's basically a narrated PowerPoint. It's worth your time to just listen to that and consider some of the examples that are given. They may help you identify root causes that are part of the case that you're analyzing. Finally, I'd like to wrap up my comments this week by watching this video of a structural collapse. This is from FDNY. And you can see here that they're operating likely post-fire. In other words, there's not a lot of active burning going on. This has become an exterior operation only. We know that as a fundamental guideline for fire suppression tactics that we choose one or the other. We either suppress the fire from the outside or from the inside. And you can see they're operating these elevated master streams from the outside. So this is late in the game in terms of the fire. Construction of this building, this could be a Class 3 building. However, I think that's unlikely given the height. So it's masonry exterior walls. A Class 3 building would have wood framed floor and roof structures. This would probably be getting a bit tall for that type of construction. This is probably a masonry constructed building with floor structures of concrete and steel, something of that nature. What I want you to pay attention to as you watch this is the rate at which water is being applied to the structure. So you can see they're operating these elevated master streams. Typical discharge from a nozzle of that type is going to be somewhere between 1 and 2,000 gallons per minute. Now, a good rule of thumb for the weight of water, it's 8.3 pounds per gallon. So if you think about that master stream discharging 2,000 gallons per minute, you're putting about 17,000 pounds of water on this structure every minute. If that water can't drain to the ground, it's going to accumulate in those high floors, and you're adding a substantial live load to the structure. So tactically, one of the things you need to think about is if we've gone to this route of using an elevated master stream, we got to create some way for that water to get out. And that may be a matter of propping open stairway doors so the water can cascade down the stairs. There have been cases, I think about a fire here in the city of Madison where they had a 4 or 5 story condo type structure burning. They're using an elevated master stream. Prior to initiating that attack with the master stream, they actually sent crews in with the roof saws to cut scupper drains. So that's a drain in the wall that's right at the base of the wall, right where the floor and the wall meet, and the water can pour out of that, again, to minimize that live load that they're adding to the structure. Irrespective of what tactic you use while you're actually in the act of suppression, another thing that you need to think about is re-entry to that structure after those heavy streams have been used. We may have to re-enter that structure for a number of reasons. We may have to assess the structural integrity of the building to see if it's something that we can leave and just board up, or if we need to bring in heavy equipment to bring the building down. Our investigator's going to have to get in there at some point to have a look around. There are, a number of reasons that we might need to go back inside this structure. One of the good guidelines is that you should avoid re-entering a structure that a master stream has been used on for some period of time to allow the water to drain off. And it kind of depends on who you ask, how long that should be. I would say certainly not less than 15 minutes. The structure should be allowed just to sit, and the water should be allowed to run down through cracks and crevices and pathways through the building to try to diminish that live load. So that'll conclude my comments for this week. As always, if there's anything I can do to assist your learning, please feel free to get in touch with me at the contacts listed in the syllabus.